Now we turn to the third vector space associated with a matrix. The null space of a matrix A is the set of vectors U such that A times U is the zero vector, and it's written null of A. So, for example, this matrix times the vector 0, 0, 0 is the zero vector, so the null space of this matrix includes 0, 0, 0. That's pretty trivial. Here's another example. This matrix times 6 minus 1 minus 1 is the zero vector. So the null space also includes 6 minus 1 minus 1. By the dot product definition, the product of a matrix with rows A1 through AM with the vector U is a vector whose entries are the dot products of those rows with U. So a vector U is in the null space of a matrix with rows A1 through AM if and only if U is a solution to the homogeneous linear system A1.x equals 0 through AM.x equals 0. So we just saw the null space of a matrix with rows A1 through AM equals the solution set of the homogeneous linear system. So this shows that the null space is, in fact, a vector space. But let's show that in a different way, directly, by showing that it satisfies the algebraic properties of vector spaces. Property V1 requires that the set include the zero vector. Well, since A times a zero vector is always a zero vector, the null space does contain a zero vector. Now for property V2. If U is in the null space, then for any scalar alpha, A times the scalar alpha times U equals alpha times A times the vector. A times the vector is the zero vector. So this is alpha times the zero vector, which is 0, which shows that alpha U is also in the null space. Finally, for property 3, if U is in the null space and V is in the null space, then A times the sum of U and V can be split up as A times U plus A times V. Since each of U and V are in the null space, each of these is a zero vector, so their sum is also a zero vector. That proves V3, that the sum of U and V is in the null space of A. So this shows that the null space of A is a vector space. Earlier we saw that if you have a solution U1 to a linear system, then the solution set of that linear system can be written as U1 plus big V, where big V is the solution set of the corresponding homogeneous linear system. We can restate that in the language of matrices. If U1 is a solution to the matrix vector equation A times x equals B, then the solution set of this matrix vector equation is U1 plus big V, where big V is the null space of A. Let's look at some simple but important consequences of this proposition. If the vector space big V, which is defined to be null A, is a trivial vector space, then the solution U1 is the only solution to this matrix vector equation. And if big V is not trivial, then U1 is not the only solution. So as a consequence, we get that the matrix equation A times x equals B has at most one solution if and only if the null space of A is a trivial vector space. Now, how can we tell if the null space of a matrix is a trivial vector space? The answer to that will have to wait.